Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Density. Density is defined as mass per unit volume. We can express density with the symbol ρ and the following equation. ρ equals m divided by v, where ρ is density in kilogram per cubic meter or grams per cubic centimeters. M is mass in kilogram or gram. V is volume in cubic meters or cubic centimeters. Density is specific value for each material, meaning that same material will always have the same density. For example, let's say we know an unknown material with a mass of 2.41 kg and its volume of 125 cubic centimeters. To determine which material our unknown material is made of, we know the densities of gold, aluminum, and silver as shown in the table. Convert the mass from kilograms to grams first, as 2.41 times 1000 is equal to 2410 grams. So, the density of unknown material equals 2410 grams divided by 125 cubic centimeters equals 19.3 grams per cubic centimeters. Therefore, our unknown material is made of gold. The density of an object can explain whether it will float or sink in a liquid. If the density of an object is more than the density of liquid, the object will sink. If the density of an object is less than the density of the liquid, the object will float. For example, a block of aluminum will sink and settle to the bottom of a liquid. This shows that aluminum's density is more than liquid's density. A block of ice will float at the surface of liquid, but will be totally submerged. This shows that ice's density is equal to the liquid's density. A block of cork will float at the surface of a liquid, with some of it submerged. This shows that cork's density is less than liquid's density. Experiment to investigate the density of a regular object. 1. Measure the mass of a regular object using an electric balance, or a Newton meter. If a scale balance is used, the reading will be the mass of the regular object. If a Newton meter is used, the reading will be the weight of the regular object, then dividing it by 10 to get its mass. 2. Find the volume of a regular object by measuring its dimensions and calculating the volume using the formula. For example, a cube, measure the length of each side with a ruler. Calculate its volume using V equals side cubed. A cuboid, measure the length, width and height with a ruler. Calculate its volume using V equals length times width times height. A cylinder, measure the height with a ruler. Measure its diameter using a ruler and wooden blocks as shown. View the top and measure the distance between blocks at different positions to check for consistency. Calculate the radius of the cylinder by dividing the diameter by 2. Calculate the volume of cylinder using V equals pi r squared h. A sphere, measure the radius using the same method as for the cylinder. Calculate the volume of the sphere using V equals 4 over 3 pi r cubed. We should measure each length at different positions, and find the average to get an accurate value. View the scale at a perpendicular angle to avoid parallax error. 3. We can calculate the density of each object using ρ equals m divided by v. Experiment to investigate the density of an irregular object that sinks in water, such as a stone. 1. We measure the mass of a stone using an electric balance, or a Newton meter as shown. 2. We measure the volume of a stone using a measuring cylinder, as follows. Fill the measuring cylinder with water. Read the initial volume, V1, by viewing the scale at perpendicular angle at the bottom of the meniscus as shown. Carefully place the stone into the water. The water level rise, as shown. Read the final volume, V2, by viewing the scale at a perpendicular angle at the bottom of the meniscus. The volume of the stone is the final volume, V2, minus the initial volume, V1. 3. We can calculate the density of a stone using ρ equals m divided by v. How to determine the volume of a piece of wood that floats in the water, such as a cork. Fill a measuring cylinder with water. Tie a thread to a stone, and place it into the water. Read the initial value, V1, by viewing the scale at a perpendicular angle at the bottom of the meniscus as shown. Remove the stone from the measuring cylinder by lifting it up by the thread. Tie the cork to the end of the thread. Lower the cork and stone into the measuring cylinder. Read the final volume, V2, by viewing the scale at a perpendicular angle at the bottom of the meniscus as shown. The volume of the cork is the final volume, V2, minus the initial volume, V1. Pressure. Pressure is defined as a force per unit area. We can write the equation of the pressure as P equals F is divided by A, where P is the pressure in Newton per meter squared or Pascal. F is a force in Newton. A is the area in meter squared. Pressure of a solid object on the contact surface area. A cuboid solid has dimensions as 3 meters, 2 meters, and 5 meters. It laying on the contact surface, and its weight of 500 newtons exerts on the contact surface area of 3 meters by 2 meters. The contact surface area is 3 times 2, which it equals 6 meters squared. The force is the weight of the cuboid. The pressure can calculated using force divided by area. So, the pressure is 500 divided by 6, which it equals 83 Pascal. The same cuboid solid is laying on the contact surface. Its weight of 500 newtons exerts on the contact surface area of 3 meters by 5 meters. The contact surface area is 3 times 5, which it equals 15 meters squared. So, the pressure is 500 divided by 15, which it equals 33 Pascal. The same cuboid solid is laying on the contact surface, and its weight of 500 newtons exerts on the contact surface area of 2 meters by 5 meters. The contact surface area is 2 times 5, which it equals 10 meters squared. So, the pressure is 500 divided by 10, which it equals 50 Pascal. We can conclude the minimum pressure is 33 pascals, when the largest contact area, while force remains the same. And the maximum pressure is 83 pascals, when the smallest contact area, while force remains the same. From this information, we can conclude that the pressure increases as the contact area decreases while the force remains the same. In the opposite way, the pressure increases as the force increases while the contact area remains the same. An application of pressure in everyday life. When large pressure is due to the small area. For example, the spikes on soccer shoes reduce the area of contact. This increases the pressure, providing the soccer players with a better grip on the ground. Knives, scissors and saws are all used to cut objects, because they have sharp edges that create a small area of contact, resulting in high pressure that helps to cut the objects easier. The shovel's sharp edge creates a small area of contact with the ground, resulting in a high pressure that helps to dig the soil easier. When small pressure is due to the large area. For example, a wooden plank increases the surface area of contact with the soft ground, which reduces the pressure and prevent the wheelbarrow from sinking on the soft ground. The wider shoulder pad has a large area, which reduces the pressure that acts on the shoulder. The elephant and the polar bear have big feet, which creates a large surface area of contact with the soft ground or snow. This reduces the pressure, so they do not sink too deeply. Pressure in a liquid. Pressure in a liquid acts on an object in all directions. The pressure is higher at the greater depths in the liquid, resulting in a higher force acting on an object compared to shallower depths. Pressure decreases as the object rises through the liquid. The equation of pressure in a liquid is P equals rho g h, where P is pressure in newtons per meter squared or pascals. Rho is the density in kilograms per cubic meter. G is the acceleration due to gravity, equal to 10 meters per second squared. H is the depth in meters. We can conclude from this equation that the pressure in a liquid depends on the density of a liquid and the depth in a liquid. We can prove this formula. If the container is filled with a liquid, the pressure in the liquid at the bottom of the tank is the force divided by the base area. The force is the weight of a liquid, which is equal to the mass of the liquid multiplied by gravity. The mass of the liquid is density of liquid multiplied by the volume of the container. The volume of the container is equal to the depth multiplied by the base area. So, the pressure at the bottom is equal to F over A. By substituting the force, F, with W equals mg. Substituting the mass, m, with rho v. And substituting the volume, v, with h, a. We can derive the equation P equals rho g h. The pressure in a liquid depends on the density of a liquid and the depth in a liquid. Consider two containers filled the same liquid and having the same depth. The pressure at the bottom of the liquid in both containers is the same because the liquid has the same density and depth. It is not affected by the size of the containers. The container has three holes labeled as A, B, and C, which cause the liquid to flow out of the container. The liquid flows out of the container at point C further than B and A because point C experiences a higher pressure due to its greater depth. Conversely, the liquid flows out from point A over the shortest distance because point A is shallower and has the lowest pressure. A barometer is a device used to measure atmospheric, or air, pressure. A simple barometer was made by filling a long glass tube with mercury, and then inverting it into a bowl of mercury. The mercury falls until the weight of the column is supported by the air pressure pushing down on the mercury in the bowl as shown. This creates a vacuum at the top of the tube, which has zero pressure. As a result, the air pressure outside the tube acts on the mercury surface, pushing it up the tube to a height that balances the weight of the mercury column. So, the air pressure acts on the surface of mercury to equal the mercury pressure in the column at the same level. If the column of mercury is 0.74 meters high, what is the air pressure? The density of mercury is 13,600 kg per cubic meters. Take the gravitational field strength as 10 Newton per kilogram. The air pressure is equal to rho g h. To substitute rho equals 13,600, g equals 10, and h equals 0.74. So, P equals 100,000 pascals. Air particles at the top of the tube reduce the mercury column height, causing the barometer to underestimate the true air pressure. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. States of matter. Any matter can exist in one of three states: solid, liquid, or gas. The particles that make up matter can be atoms, molecules, ions, or electrons. Solids. Here is called particle, atom, or molecule. The intermolecular forces between particles in a solid are very strong. This causes the particles to be very close together and arranged in a regular pattern. The particles in a solid can only vibrate about fixed positions. Solids have a definite shape and a definite volume, because its particles cannot move freely and are not easily compressible. Liquids. The intermolecular forces between the particles in a liquid are slightly weaker than those in a solid. This causes the particles to be close together, but not arranged in a regular pattern. The particles in a liquid can move and slide past each other. Liquids have no definite shape, but do have a definite volume, because its particles can flow to take the shape of their container, but they are not easily compressible. Gases. The intermolecular forces between the particles in a gas are very weak. This causes the particles in a gas to be far apart. The particles in a gas can move around randomly at high speeds. Gases have no definite shape and no fixed volume, because its particles can move freely to take the shape of their container and are highly compressible. Internal energy of matter. This section is the extra knowledge. Internal energy is the sum of random kinetic energies and potential energies of molecules. Kinetic energy of molecules in matter depends on its temperature. This means that kinetic energies of molecules increase as temperature increase. Therefore, kinetic energy of gases are greater than liquids, and kinetic energy of liquids are greater than solids. Potential energy of molecules in matter depends on the space between molecules. This means that potential energy of molecules increase as the separation between molecules increase. Therefore, potential energy of gases are more than liquids, and potential energy of liquids are more than solids. Change in states of matter. When a solid is changed into a liquid, this process is called melting. Liquid is changed into gas, this process is called boiling or evaporating. Gas is changed into liquid, this process is called condensation. Liquid is changed into solid, this process is called freezing. Melting processes. The solid at the melting point absorbs thermal energy to break the intermolecular forces and separate the molecules, so the potential energy increases. While the temperature is constant at melting point, so kinetic energy of molecules remain constant. Therefore, the internal energy increases when solid is changed into liquid. Boiling processes. The liquid at the boiling point absorbs the thermal energy to break the intermolecular forces and separate the molecules, so the potential energy increases. While the temperature is constant at boiling point, so kinetic energy of molecules remain constant. Therefore, the internal energy increases when liquid is changed into gas. Freezing processes. The liquid at melting point removes the thermal energy to create the intermolecular forces and reduce the separation between molecules, so the potential energy decrease. While the temperature is constant at freezing, so kinetic energy of molecules remain constant. Therefore, the internal energy decrease when liquid is changed into solid. Condensing processes. The gas at boiling point removes the thermal energy to create the intermolecular forces and reduce the separation between molecules, so the potential energy decrease. While the temperatures is constant at condensing, so kinetic energy of molecules remain constant. Therefore, the internal energy decrease when gas is changed into liquid. Cooling and heating of matter. Cooling processes. Cooling occurs when the temperature of matters decrease, causing the thermal energy is removed from matters. This causes kinetic energy of molecules decrease. While potential energy of molecules remain constant, or a bit decreasing due to compression, because the separation between molecules also remain constant, or a bit decreasing due to compression. Therefore, the internal energy of matters decrease. When the water at initial temperature of 80 Celsius is cooling until equilibrium to the room temperature of 25 Celsius, the resulting show as the graph of temperature in Celsius against time in seconds. The rate of decrease in temperature at the initial is greatest because the high different temperature between the water and surrounding, so more thermal energy loss to surrounding. The rate of decrease in temperature at the final is lowest because the small different temperature between the water and surrounding, so small thermal energy loss to surrounding. Heating processes. Heating occurs when the temperature of matters increase, causing the thermal energy is added to the matters. This causes kinetic energy of matters increase, while potential energy of molecules remain constant, or a bit increasing due to expansion, because the separation between molecules also remain constant, or a bit increasing due to expansion. Therefore, the internal energy of matters increase. When the water at initial temperature of 25 Celsius is heated until temperature of 80 Celsius, the resulting show as the graph of temperature in Celsius against time in seconds. The rate of increase in temperature at the initial is greatest because the small different temperature between the water and surrounding, so less thermal energy loss to surrounding. The rate of decrease in temperature at the final is lowest because the more different temperature between the water and surrounding, so more thermal energy loss to surrounding. Here is the graph that shows the relationship of change in temperature in degrees Celsius and time in second of the water at sea level of atmospheric pressure. Between -10 and 0 Celsius, the water is a solid state as ice. It is heated. At 0 Celsius, the ice melts and becomes liquid. There are the solid to mix with liquid in this section. At melting, the temperature is constant because the ice absorbs latent heat to break the intermolecular forces and separate molecules, causing the potential energy increase, while kinetic energy of molecules remains constant. The latent heat is the energy required to change the state of a substance. Between 0 and 100 Celsius, the water is a liquid state. It is heated. At 100 Celsius, the water boils and change becomes from vapor. There are the liquid to mix with gas in this section. At boiling, the temperature is constant because the water absorbs latent heat to break the intermolecular forces and separate molecules, causing the potential energy increase, while kinetic energy of molecules remains constant. Between 100 and 120 Celsius, the water is a gas or vapor. It is heated. Specific heat capacity of water is more than ice and the specific heat capacity of ice is more than vapor. This means that it takes more energy to raise the temperature of water by 1 degree Celsius than it does to raise the temperature of ice or vapor by 1 degree Celsius. This causes the graph between 0 and 100 Celsius is least steep and the graph between 100 and 120 Celsius is most steep. In reverse process, when a vapor at 100 Celsius removes the thermal energy and change states from gas into liquid, which is called condensation. At condensation, the temperature is constant because the gas removes latent heat to create the intermolecular forces, causing the potential energy decrease, while kinetic energy of molecules remains constant. When a water at 0 Celsius removes the thermal energy and change states from liquid to solid, this is called solidification or freezing. At solidification, the temperature is constant because the water removes latent heat to create the intermolecular forces, causing the potential energy decrease, while kinetic energy of molecules remains constant. Boiling and evaporation. Boiling occurs when a liquid reaches its boiling point and continues to absorb energy to break the intermolecular forces and separate molecules. This causes the potential energy of the molecules increase, while their average kinetic energy remains constant and temperature also remains constant. Evaporation occurs when the most energetic molecules at the surface of a liquid break the intermolecular forces and escape from the liquid surface into the air. This leaves the lower energies molecules behind, which causes the temperature of the liquid to decrease. The similarity between boiling and evaporation is the both processes to change states from liquid into gas. The difference between boiling and evaporation. Boiling occurs only at the boiling point of a liquid, while evaporation occurs at any temperature between melting and boiling points. Boiling occurs throughout the liquid, producing bubbles, while evaporation occurs at the surface of the liquid. Temperature remains constant during boiling, while temperature decreases during evaporation. Factors that affect the rate of evaporation. Temperature. The higher the temperature, the faster the rate of evaporation. This is because there are more the most energetic molecules at the surface that can escape into the air. Surface area of liquid. The larger the surface area of the liquid, the faster the rate of evaporation. This is because there are more the most energetic molecules at the surface that can escape into the air. Wind speed. The faster the wind speed blows over the surface of liquid, the faster the rate of evaporation. This is because the wind removes the water vapor from the surface of liquid, allowing more water vapor escape. Humidity. The lower humidity, the faster the rate of evaporation. This is because there are less water vapor in air, allowing more water vapor escape. When an object is heated, its temperature increases. This causes the average kinetic energies of all particles in the object to increase. The potential energy of particles may remain constant, or increase slightly due to expansion, because the separation between particles may also remain constant, or increase slightly due to expansion. Therefore, the internal energy of the object increases. This internal energy is also known as the thermal or heat energy. The thermal energy, delta E, added to an object of mass, m, to increase its temperature, delta T, can be written as the equation delta E equals mc delta T, where delta E is the thermal energy in joules, m is the mass in grams or kilograms, C is the specific heat capacity of the substance in joules per gram degree Celsius, or joules per kilogram degree Celsius. Delta T is the change in temperature in degrees Celsius or kelvins. Specific heat capacity, C, is defined as the thermal energy that required per unit mass to increase the temperature by 1 degree Celsius or Kelvin. It remains constant for a given substance. The experiment to measure the specific heat capacity of a metal block. We set up the apparatus as shown in the diagram. The thermometer is used to measure the change in temperature. The heater is used to supply heat to the metal block. It is connected to a voltmeter and an ammeter to measure the power input. The metal block is insulated with an insulating material such as rubber, plastic, or cloth to reduce thermal energy loss to the surroundings. The stopwatch is used to measure the time it takes for the temperature to change. The procedure of measuring the specific heat capacity is as follows. First, measure the mass of the metal block using a scale balance. Second, turn on the heater and wait for it to reach the maximum heat. Then, start the stopwatch and record the initial temperature, T1. Third, read the voltage, V, on the voltmeter and the current, I, on the ammeter. Fourth, time the interval for T seconds, then record the final temperature, T2. Fifth, calculate the thermal energy added to the metal using the equation, delta E equals P multiplied by T, where P is the power input, which P equals voltage, V, times current, or I. Therefore, C equals delta E over M delta T. And substitute delta E2, V, I, T. Delta T equals T2 minus T1. Specific heat capacity, C, calculated from this experiment will be more than the actual value of the metal block, because some of the thermal energy is lost to surroundings, causing a smaller change in temperature. The experiment to measure the specific heat capacity of a liquid. We set up the apparatus, as shown in the diagram. The apparatus are changed at the insulated container that fills with a liquid. There is an insulated lid to reduce thermal energy loss to the surroundings. The procedure of measuring the specific heat capacity of a liquid is the same as for a solid, with the following changes. The mass of the liquid is measured by weighing the empty insulated container, and then weighing the container with the liquid. The difference in mass is the mass of the liquid. The specific heat capacity is calculated using the equation C equals delta E over M delta T, where delta E is the thermal energy added to the liquid. M is the mass of the liquid. Delta T is the change in temperature. I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.